Hello, this is Richard Hammack's Calculus 1. We are in part 4 of the course on applications of derivatives. This is lecture 31 on what is called local extrema and the first derivative test. Roughly speaking, our goal in this lecture is going to be to find the high and low values of a function in a manner that I'll make precise shortly. But first, a recap of lecture 30. Remember that a function f increases where f prime of x is positive and decreases where f prime of x is negative. So in this f of x, it's decreasing right here, and those slopes are negative, so the derivative is negative. Where it's increasing, those slopes are positive, so the derivative is positive, and so on. We had a big definition. A critical number c in the domain of a function f is called a critical point of f if either f prime of c equals 0 or f prime of c is undefined. So for instance, this number c right here is a critical point because f prime of c is undefined. There's no tangent line right there. Here's a c that's a critical point because f prime of c equals 0. It's the slope of that horizontal tangent. Here's another critical point of our function. F prime of this c equals 0. And here's a fourth critical point. F prime of this particular c is not defined. Remember that if f of c is defined, that is, you can plug c into the original function f, then if f changes from increasing to decreasing at c, then c is a critical point of f. Right here, at this c, the function changed from increasing to decreasing, and that's a critical point. Changing from increasing to decreasing, it happens at a critical point. And the same if f changes from decreasing to increasing at c, then c has to be a critical point of f. So changing from decreasing to increasing, that happens at a critical point. Changing from decreasing to increasing, it happens at a critical point. All of this is the main content of lecture 30. So let's move on. We'll start out today with a couple of big definitions that we'll be working with for the rest of this lecture and considerably after this lecture as well. Suppose c is a number in the domain of f. We say that the y value f of c is a local maximum of f if f of c is greater than or equal to f of x for all x near c. So for instance, here's a function f of x, and this y value f of c right there, that would be a local maximum of f by this definition, because if you look at f of c, it's greater than or equal to f of x for any x that's near c. Plug in this x right here, f of x is a little bit less than c. So this is a local maximum. And likewise, this y value right here is a local maximum, because if you look at f of c, it's greater than or equal to the nearby f of x values. In fact, it's equal to f of c if x equals c. So that's why we say greater than or equal to. A local maximum, as you can see, is the top of a hill in a function. We call them local maximums because they may not be the highest value of the function, but they're higher than nearby points. Locally, they're the highest. This is not the highest point on the function. Instead, it's over here. But still, we call this a local maximum. At c, the function stops increasing and starts decreasing when you have a local maximum of f of c. So it stops increasing and starts decreasing at that local maximum. It stops increasing and starts decreasing at this local maximum. There's a companion definition. We say a y value f of c is a local minimum of f if f of c is less than or equal to f of x for all x near c. Just the reverse of what we had up here. So for instance, in this picture, this y value, f of c, would be a local minimum because if you look at f of c, it's less than or equal to any nearby f of x. F of c is less than or equal to f of x for all x near c. A local minimum, you could think of it as being the bottom of a valley of your function. Way down here where the function bottoms out, that's a local minimum. And when you have a local minimum at c, the function stops decreasing and starts increasing. It was decreasing, and then at c, it started increasing. That characterizes a local minimum. Collectively, a local maximum or minimum is called a local extremum. So you would say this is a local extremum, that's a local extremum, and this is a local extremum. The plurals of these words are local maxima, local minima, and local extrema. So these are two local maxima, and we have two local maxima, and there are three local extrema indicated here. It's important to note that a local extremum technically is a y value f of c, like this f of c is a local maximum, and we say it occurs at an x value c. So this local maximum occurs at this x value of c. And a key observation here is that local extrema, they occur at critical points because they happen where a function switches from increasing to decreasing or decreasing to increasing. So they happen at critical points. They occur at critical points. So this is our big definition for today. We will be concerned with finding the local maxima and local minima of functions in today's lecture. And to do that, there is a technique called the first derivative test that locates all the local extrema of a function. And it's kind of stating the obvious when you write it down. It's very easy to understand. It works like this. Here's the first derivative test, and its purpose is to identify local extrema. Suppose C is a critical point of f, like perhaps here, 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 or here. The first derivative test states three things. First of all, it says that if f prime goes from positive to negative at c, then f of x has a local maximum of f of c at c. And this should be really obvious when you look at the picture. Right here at this c, f prime goes from positive to negative, and that's where the function was increasing and then started decreasing, so that's a local maximum. Right here, f prime goes from positive to negative at that c. The function f stopped increasing and started decreasing there, so that's a local maximum. And when we say f prime goes from positive to negative, we mean as you go from left to right. It's positive on the left and then turns negative to the right. Likewise, for similar reasons, if f prime of x goes from negative to positive at c, the other way around, then f of x has a local minimum of f of c at the x value c. So let's see, change it from negative to positive. That happens right here. F prime was negative, then it switched to positive right there at that critical point c. And that signals a local minimum because our function was decreasing. It stopped decreasing and started increasing. So we had a local minimum. So really, I hope you see these statements, they're really just stating the obvious. There's a third statement here. What would happen if you didn't change from positive to negative or from negative to positive at C? Well, that means the sign doesn't change. It says positive to both sides or negative to both sides. And you can actually see that happening right here. Here's a critical point C. Right there, the tangent line was horizontal, so the slope is 0, so f prime of C equals 0, so that's a critical point. But look what happened at the function. It was increasing, it leveled out, and then it continued increasing. There's no local maximum there, nor is there a local minimum. The first derivative test says that if f prime does not change sign at C, like right here, then there is no local extremum at C. So 3 statements in the first derivative test, and I hope they should be very obvious and crystal clear. I should point out here that your critical points, you'll notice, you're not necessarily going to pick up a local extremum at each one. Like, for example, at this critical point, there was no local extremum. You should look at your critical points as candidates for the locations of the local extrema. You want to narrow down your search. You want to investigate each critical point and decide whether it's a local maximum or a local minimum or neither. And the first derivative test gives you the answer. This leads to a procedure that we can use to find all local extrema of a function f of x. Let's see. What would we do? First of all, we have to find the critical points. That's step 1. Those are the candidates for the local extrema. And remember, to find all the critical points, what you do is you, first of all, find f prime of x. You look at it, you identify all the c in the domain of f for which f prime of c is not defined. And such c would be a critical point of f. But you could also have some critical points where f prime of c is 0, and to find them, you'd look for the solutions of the equation f prime of x equals 0. You'd set f prime of x equals 0 and solve for x to find the c's like this one or this one where the derivative is 0. Now I should point out that you're not always going to find a critical point c for which f prime of c is not defined. Sometimes you won't find one for where f prime of c is equal to 0. But if there are critical points, one of these 2 conditions is going to hold. So that's how you find all the critical points. The next thing you want to do is use the first derivative test to test each one of those critical points. The second step is to apply the first derivative test at each critical point from step 1. And remember, if you switch from positive to negative derivative at that critical point, you've got a local maximum. If you switch from negative to positive, according to the first derivative test, you've got a local minimum. And you could do that for each of your critical points and find all of the extrema this way. So let's look at some examples. In example 1, let's find the local extrema of the function 2x cubed minus 3x squared plus 5. And we'll apply our procedure. Step 1 was to look for the critical points of f. And remember, that involves finding the derivative. F prime of x is 6x squared minus 6x. And looking at that, you'll notice that it's defined for all values of x. The domain is all real numbers, the domain of this derivative, all real numbers. So you're not going to have any critical points for which f prime of c is undefined. But you might have some critical points for which f prime of c equals 0, and to find those, you take this derivative and you set it equal to 0 and you solve it. Let's see. This factors. You get 6x times x minus 1 equals 0, and right there you see the solutions. X equals 0, would make this product 0, and also x equals 1 would make this factor 0, so the whole product equals 0. So we've picked up two critical points, 0 and 1. So that's the first step. We've found our critical points. Now remember, these are the candidates for the local extrema of this function. To figure out where we have a local maximum or a local minimum, we plot those points, 0 and 1, and we're going to look at the change in sign, if any, of the derivative around those points and apply the first derivative test. Now our derivative factors is 6x times x minus 1, so it's convenient to look at those two factors individually. 6x, it's positive when x is positive and negative when x is negative. The other factor, x minus 1, it's positive when x is greater than 1 and negative when x is less than 1. So we figured out the signs of those two factors at various points on the number line. F prime of x is the product of 6x times x minus 1. So in this interval over on the right, f prime is positive times positive, so it's positive. On this middle interval, f prime is a positive times a negative, so it's negative. And on this leftmost interval, f prime of x is a negative times a negative, so it's positive. And now we can see where our local extrema are. Notice that at the critical point 0, the derivative changed from positive to negative, so the first derivative test says we have a local maximum at x equals 0. So that's the first part of our answer. F has a local maximum at x equals 0, right there where you change from positive to negative in f prime. Now remember, that's the location of the local maximum. The actual local maximum is f of that 0, and f of 0, if you plug 0 up here, you get 5. So the local maximum is f of 0 equals 5. It's 5, but it occurs at x equals 0. At 1, the derivative changes from negative to positive. So remember what the first derivative test says about that. You have a local minimum at x equals 1. That's the location of the local minimum. It occurs right there at x equals 1. The actual local minimum is the y value, f of 1, which would be 2 times 1 cubed minus 3 times 1 squared plus 5. F of 1 equals 4. So f has a local minimum at x equals 1, and that local minimum is f of 1 equals 4. That's its y value. So we're done. We've answered the question using the first derivative test. We've found the local extrema of this f of x. Now we're done with the problem, but it's instructive to think about what the graph y equals f of x looks like. It's a cubic function. It looks like this. It goes up. You have a local maximum right there at 0. It starts going down where the derivative is negative. Have a local minimum right here at x equals 1, and then it goes up forever after that. Example 2. In this example, we'll find all the local extrema of the function f of x equals x times e to the x. Now the first step, remember, in solving this is to find the critical points of f. And to find the critical points, you need to compute the derivative. We've got to use the product rule to compute this derivative. F prime of x is, by the product rule, 1 times e to the x plus x times e to the x. And when you look at that, you can see that the domain of this derivative is all real numbers. There's no x for which this is not defined. Whatever x is, you can do e to the x and then plus x times e to the x. So you're not going to get any critical points here where the derivative is undefined. But you might have some critical points where the derivative is equal to 0, and to find them, remember, you set the derivative equal to 0 and solve. Now, let's see. We could factor here. You've got an expression equal to 0, so that's a situation in which factoring can work. You can factor an e to the x out of this. You get e to the x times 1 plus x. So this would be 0 if either one of those factors is 0. Now think about e to the x. No matter what x is, e to the x is positive. It's never 0. Sure, it gets pretty close to 0, but it's never 0. The 1 plus x, however, will be 0 when x equals minus 1. So we've picked up a critical point, and there's only one. The only critical point is x equals minus 1 because it makes that second factor 0. So good, we've completed our first step, we've found the critical points, and there's only one, so we put it on the number line, and now we're going to apply the first derivative test to that critical point. We're going to look at how the sign of f prime changes there. Now, f prime of x is e to the x times 1 plus x. It's got two factors. We'll look at them individually. E to the x is always positive, no matter what x is. And the other factor, 1 plus x, it's positive when x is greater than minus 1, and otherwise it's negative. So our derivative, f prime of x, which is e to the x times 1 plus x, on the right-hand interval, it's a positive times a positive, so it's positive. On the left-hand interval, it's positive times negative, so it's negative. And we see right here, at that critical point, the derivative changing from negative to positive. And think about what the first derivative test says about that. It says you have a local minimum. It makes sense because the function was decreasing and then started increasing. It bottomed out. So answer, f of x has a local minimum at x equals minus 1, right there at that x value. And there's no local maximum here. There's no local maximum because nowhere did this function change from positive to negative. So the first derivative test says no local maximum. So we're done. And that's pretty good for never even looking at the graph of the function. We're done, but let's quickly take a look at that function. If you graphed it carefully, it would look something like this. It's decreasing, bottoms out right there at minus 1. It starts increasing. Notice f of 0 would be 0, so it has an x-intercept right there at 0, and it increases like that. So you'll see there, sure enough, there's a local minimum at minus 1, but no local maximum. Example 3. Let's use the first derivative test to find all local extrema of the function f of x equals the cube root of x squared minus 2/3 x. Now we're going to have to find its derivative, so let's write that as a power this way. F of x is x to the 2/3 minus 2/3 x. And in finding the critical points, we've got to take the derivative of f. So let's do that. Use the power rule. F prime of x is 2/3 x to the power of 2/3 minus 1, which is negative 1/3, minus 2/3. And there's a little bit of cleanup we can do here. Let's bring that negative 1/3 exponent down as a radical. So the derivative cleans up like this. And you'll notice here it has two terms, and you can factor out a 2/3. So let's do that. So we get 2/3 times 1 over the cube root of x minus 1. That's our derivative. Now we're thinking about critical points. And you'll notice here that f prime of 0 is undefined because if you tried to plug in 0 to f, you'd be dividing, f prime, you'd be dividing by 0 right there. So just by looking at this derivative, we've picked out one of our critical points, 0, because it makes the derivative undefined. And also just by looking at this, you can find a value of x that makes this derivative equal to 0. It would be x equals 1, because 1 over the cube root of 1 is 1, and then minus 1 is 0. F prime of 1 equals 0. And you can see here that's the only value of x that would make this derivative 0. It's a simple enough expression that you can just read it off. So you can see that we have two critical points, and they are 0 and 1. 0 makes the derivative undefined, and 1 makes the derivative equal to 0. So we've got our critical points. And let's plot them right here on the number line. The next step is to apply the first derivative test to each of these critical points and see how the sign of f prime changes. We'll do something a little bit different for finding the signs of this derivative f prime. You can't really factor this any further, so it's kind of hard to look at the signs of the factors. But what we could do is we could take what you would call test points. First of all, think about this interval from negative infinity to 0 over on the left. Take a test point in there and plug that into f prime and see whether you get positive or negative, and that'll tell you the sign of f prime on this interval. Good test point would be -1. That's easy to compute. So -1 right there. Let's take f prime of -1. That would be, you'd plug -1 in up here. So that's 2/3 1 over the cube root of -1 minus 1. And this is a -1 right there. So 2/3 -1 minus 1. And that's -4/3. And that's less than 0. So since f prime of -1 was a negative number, we know the sign of this derivative is negative on that first interval. Let's move on to another interval. Let's take the interval from 0 to 1. So we'll take a test point in this interval. But you want to take test points that are easy to work with in the function. This f prime has a cube root in it, so you want to plug in an x that you could easily take the cube root of. So let's think of an x between 0 and 1 that's a perfect cube. 1/8 would work because the cube root of 1/8 is 1/2. So let's calculate f prime of 1/8. We'll plug in 1/8 into f prime here, and we get 2/3 1 over the cube root of 1/8 minus 1. And that's 2/3 of, let's see, the cube root of 1/8 is 1/2, and 1 over that is 2, so it's 2/3 times 2 minus 1. And that's equal to positive 2/3, and that's greater than 0. So we plug 1/8 into the function f prime, and we got a positive. So f prime is positive on that interval. One more interval to do. Let's take a perfect cube over in this last interval from 1 to infinity. And 8 would be a good number to pick because we know the cube root of 8, it's easy to compute, it's 2. So we'll compute f prime of 8. And that's 2/3, 1 over the cube root of 8 minus 1. 2/3 times 1/2 minus 1. And that's -1/3, and that's less than 0. It's negative. So that means f prime is negative on this last interval. And from this, we can read off, using the first derivative test, where the local extrema are. You change from negative to positive right there at 0, so you've got a local minimum at 0 by the first derivative test, and you change from positive to negative right here. So the first derivative test says that's a local maximum right there at 1. So our answer, f has a local minimum at x equals 0, and that minimum would be the y value f of 0, which if you plug it in up here is 0. And f has a local maximum at x equals 1. And that maximum would be f of that x value, which is 1/3. If you plug in 1 here, you get f of 1 equals 1/3. So one local minimum at x equals 3rd, and that minimum is one local minimum at x equals 0, and that minimum is f of 0, and one local maximum at x equals 1, and that maximum is the y value f of 1 equals 1/3. So we're done with the problem. We've used the first derivative test to find the local extrema of this function. Now, if you wanted to graph it, f of x looks something like this. It's decreasing down to that local minimum of 0 right there. Then it starts increasing. You got a little local maximum right here at x equals 1. and that's a height of 1/3, and then the function f starts going down after that. So a local maximum here and a local minimum there. Example 4. Let's find all the local extrema of the function f of x equals 1 over x squared, which you might want to write as x to the power of minus 2. So we know to look for the critical points, we take f prime of x, it's minus 2x to the minus 3. That's minus 2 over x cubed. And right there, that's so simple. You can automatically tell the sign of f prime. If x is positive, minus 2 over that positive number cubed is a negative number. And if x is a negative number, minus 2 over that negative number cubed is a positive number. So f prime of x is negative when x is positive, and positive when x is negative. Now watch out. You get a sign change right there at x equals 0. But don't jump to judgment. It turns out that there are no local extrema here. And why not? Why is there not a local maximum at x equals 0? Well, it's kind of subtle, but you really need to be aware of these types of situations that are happening here. That number 0, we never said it was a critical point. In fact, 0 is not even in the domain of f. So that 0 that was right there, it's not a critical point. It's not in the domain of f. Remember, a critical point has to be in the domain of your function, and 0 isn't. So no local extrema because we have no critical points for them to occur at. If you graph this function, f of x equals 1 over x squared, well, actually, I think you know what that looks like. It looks like this. And right there where you're maybe thinking you might have a local maximum, you actually have a vertical asymptote. So there's no f of 0 to give you a maximum. So watch out for situations like this. Your critical points need to be in the domain of the function. And if we lose sight of that, we can sometimes make mistakes and come up with erroneous answers. We wouldn't want to say there's a local maximum at 0 here when there actually isn't. Example 5. Let's find all the local extrema of the function f of x equals x plus sine x. So our process is to, first of all, find the critical points of this function. So let's take f prime of x, and it's 1 plus cosine of x. And you'll notice that the domain of both f and f prime is all real numbers. And there are no values of x, therefore, that make f prime undefined. So you're going to have no critical points at which the derivative is undefined. But you might have some for which that derivative is equal to 0. And to find them, you set the derivative equal to 0 and you solve. 1 plus cosine x equals 0 can be written as cosine x equals minus 1. And so there we're looking for the values of x for which cosine x equals minus 1. You would interpret x as a radian measure because it's plugged into cosine. And thinking of the unit circle, you know the values of x that make cosine of x equals minus 1. Cosine of pi is minus 1, and then plus any even multiple of pi. So the critical points, the solutions of this equation, cosine x equals minus 1, are pi, right there, plus k times 2 times pi, which is pi times 1 plus 2k. And this is for k, a positive or negative integer. So you're picking up infinitely many critical points here. Pi, pi plus 2 pi, pi plus 4 pi, pi plus 6 pi, and so on. And you could look at this as being as follows. The critical points are all the odd multiples of pi, because 1 plus 2 times an even number k is an odd number, so you pick up all the odd multiples of pi this way. So infinitely many critical points, so we're going to plot them all on the number line, all of the odd multiples of pi, 1 pi, 3 pi, 5 pi, negative 1 pi, negative 3 pi, negative 5 pi, and so on. And we want to look at the sign of the derivative at each of those critical points and see how it changes sign. So the first derivative test can tell us whether we have a local maximum or local minimum at each of these critical points. So let's think about that. An interesting thing happens here. Look at f prime of x. It's 1 plus cosine of x. That can never be negative, because remember, cosine of x can get as small as negative 1, but that can't turn this 1 negative. The best it can do is give you 1 plus negative 1 is 0. Cosine x never gets less than negative 1. So 1 plus cosine x is going to be positive, no matter what x is, except at these odd multiples of pi at which it's equal to 0. So we have here a situation in which the derivative never changes sign. At each critical point, it's positive on either side. So the first derivative test says that there are no extrema, no local extrema at all. So what's going on here? What does this function look like? If you graphed our function f of x equals x plus sine of x, it has an interesting shape. Think about this, that dotted line, that's the graph of y equals x, and you're adding sine of x to it, which is going to add something above and below, and above and below. It's just going to wiggle up that 45-degree line like this. And notice that right at, say, pi, right there, you're getting a horizontal tangent. So the derivative is equal to 0 there. But the function just keeps rising through that critical point. Right here at 3 pi, you get a horizontal tangent. The function just keeps rising through that. So every once in a while, you'll have situations like this where you expect to find extrema because you have so many critical points. But in this case, there just aren't any. So we've looked at 5 examples, and as always, you should test your knowledge and practice these problems and hone your skills by working other exercises in the textbook. That's it for today. As a recap, we've got this first derivative test for finding all local extrema. So get some practice on that. Next up, we're going to talk about 2 topics. In 32a, we'll talk about the second derivative and how that influences what's called the concavity of a function. And then in 32b, we'll have what's called the second derivative test. And that's an alternate to the first derivative test. It'll do the same thing the first derivative test does, but it's going to do it in a slightly different way with the second derivative. So that's coming up. I'll see you then, and goodbye.